Hi everyone, my name is Astrini and today I'm going to discuss about the tutorial 7 for MA3005, a course in control theory here at Nanyang Technological University. Basically, I've covered problem 1 on root locus in class, and now I'm going to discuss more on problem 2 in this following video. So for problem 2, we are asked to sketch the root locus of a system that is given as a block diagram that has a forward loop block of k multiplied by s plus 1 divided by s multiplied by s squared plus 2s plus 6. And then there's a feedback given to the system which has a block diagram of 1 over s plus 1 at the feedback. And this is going to be a negative feedback. And I'm going to complete everything with the input and the output. So first of all is to sketch the root locus for the system given in this following block diagram. And then the second part is to find the closed loop poles for k equals to 5. And as a quick recap, root locus is basically a plot of all the open loop poles and zeros for k from 0 to infinity. So it acts as a design tool for us to be able to observe or quickly identify the location of the roots, the location of the poles of a system by varying the k values. And there are a few steps that is required for us in order to be able to plot the root locus manually. First of all is we have to find the start and end points of the root locus. And again, the starting points is always from the open loop poles and the ending points are always at the open loop zeros. And in the event where the number of open loop zeros is less than the number of open loop poles, that means the ending points are at infinity. So some of the open loop poles will end at the infinity. And back to our problem here, first we have to find the open loop transfer function, which is basically k multiplied by s plus 1 divided by s multiplied by s squared plus 2s plus 6. And then there's 1 over s plus 1 at the forward loop, at the feedback loop. And if I cross s plus 1 at the bottom and at the top, what I will get is k over s multiplied by s squared plus 2s plus 6. So we can identify our zeros and poles for this open loop transfer function. And the starting points are at the open loop poles, which are equal to s equals to 0. By solving the denominator equal to 0, we get s equals to 0 and s equals to minus 1 plus minus j 2.2361. So those are our open loop poles or our starting points. And next, the ending points are at the open loop zeros. And if we look at this open loop transfer function, we can see that there is no real zeros associated, so the ending points will be at infinity. And in this case, all the three poles or or all the three starting points will end at infinity. And we have completed the first part required to plot a root locus, and we're going to move on to the second part. The second step that we need is to find the angle of departure. The angle of departure basically means the angle of departure of the root locus from the poles. And as we know, the root locus is always symmetrical about the x-axis or the real axis. So what we need to do is to find the angle of departure of all the poles located either at the top of the real axis or at the bottom of the real axis. And people usually find the angle of departure for the top section of the real axis and then just copy everything down as a mirror image about the x-axis. And let us draw a quick sketch over here. And what we have is a pole at 0, and then a pair of poles at -1, plus minus 2.2361. So we have a pair of poles at those points. And first, we're gonna find the angle of departure at the first pole, which is 0. I'm sorry. I'm gonna find the angle of departure from P1, which is -1 plus 2.2361. So that is the first angle of departure that I'm going to find. And first, we draw the line connecting P1 to other poles. So we have those two lines. And then we take the angle from the associated pole to P1, measured from the positive x-axis on that pole. So we have θ1 over here, and then the second one is we have θ2 over here. So the angle is always measured from the x-axis associated with the pole to the line connecting the pole to the pole that we want to find the angle of departure. So it's from other pole to the angle of departure pole. And the formula given is θ0, which is the angle of departure from P1, is given as 180 degree minus summation of angle of departure from P1 to other poles plus summation of angle of departure from P1 to other zeros. So we have θ0 equals to 180 degree minus the first one over here, which is 90 degree plus tangent inverse of, basically it's this angle over here. So the tangent inverse of this angle equals to the length at the x-axis, which is 1 divided by this length over here, which is 2.2361. And then we also have minus 90 degree from θ2. and we get theta naught equals to minus 24.1 degree. So that is our angle of departure from P1 for the root locus. And now we're done with the angle of departure, and next we need to find the asymptotes. So the number of asymptotes is given by the number of roots in the characteristic equation. And please be very, very careful again. You need to know the differences between an open loop transfer function and a closed loop transfer function. And a characteristic equation is always associated with the closed loop transfer function. So the number of asymptotes is equal to the number of roots in the characteristic equation or the number of closed loop poles. So those are the number of asymptotes. And of course, we need to find the characteristic equation for this problem. And what we have is CS over RS equals to forward loop transfer function over 1 plus open loop transfer function for a negative feedback system. And what we have is Ks plus 1 over S multiplied by S squared plus 2S plus 6 divided by 1 plus Ks plus 1 over S multiplied by S squared plus 2S plus 6 multiplied by S plus 1. Crossing those two terms, we have Cs over Rs equals to Ks plus 1 over S multiplied by S squared plus 2S plus 6 plus K. So that is our closed loop transfer function, and we know that there are 3 roots associated in the characteristic equation. So we have 3 roots in CE and 3 asymptotes. So now let us find the angle of asymptotes and the point of intersections among all the 3 asymptotes, and I'm going to continue on the next piece of paper. So we want to find the angle of asymptotes, and this is given by plus minus 180 degree multiplied by 2q plus 1 . Is it focusing? Okay. And so the angle of asymptotes is equals to plus minus 180 degree multiplied by 2q plus 1 over n minus m. And q is basically just an integer from 0, 1, and so on until, so we just increase q starting from 0, 1, 2, 3 until we get the total angle of asymptotes required for all asymptotes available. And n is basically the total number of open loop poles, and m is equals to the number of open loop zeros. So now we have 3 asymptotes. So let us start with q equals to 0. And we have the angle equals to plus minus 180 degree multiplied by 1 divided by 3 minus 0. And we have plus minus 60 degree. So we get 2 angles over here, and we're left with 1 because we have 3 asymptotes. So let us increase q to 1 and calculate the angle of asymptotes. We get plus minus 180 degree multiplied by 2 plus 1 divided by 3. So we get plus minus 180 degree, which is essentially 180 degree. So those are the angles of our three asymptotes for the system that we have. And next, we find the point of intersection of the asymptotes denoted by sigma A, and this is equal to the summation of poles minus summation of zeros divided by the number of open loop poles minus the number of open loop zeros. And please note that these are the summation of all the values of poles and zeros instead of the number. So what I mean is that we have sigma A equals to our poles are at -1 plus j 2.2361 minus 1 minus j 2.2361 plus 0. So those are the locations or the values of our three poles. And we don't have any zeros, so we just subtract everything with 0 divided by 3 minus 0. And then sigma A is equals to minus 2 over 3. So this is the point where all three asymptotes intersect at minus 2 over 3 at the real axis. And lastly, we need the last step in order for us to plot the root locus properly, which is basically intersection of root locus with the imaginary axis. And we know that at the imaginary axis, the value of the pole is equal to S equals to plus minus j omega. This is pole at imaginary axis. So what we can do is sub in S equals to plus minus j omega into the characteristic equation and calculate for omega. And omega will give us basically the value of the pole at the imaginary axis. And previously we calculated the characteristic equation, which is equals to S multiplied by S squared plus 2S plus 6 plus K. And we set this equals to 0 and rewrite everything. We have S to the power of 3 plus 2S squared plus 6S plus K. So we sub in S equals to plus minus j omega into this equation, which is then equal to 0 equals to minus j omega cubed minus 2 omega squared plus 6j omega plus k. And then group all the real and imaginary terms together. First, we have the imaginary terms, which is equals to minus omega cubed plus 6 omega, and the real terms, which are minus 2 omega squared plus k. So solve these two terms and set them equals to 0. And by solving the first term over here, we can get minus omega cubed plus 6 omega equals to 0. So omega equals to plus minus square root of 6, which is plus minus 2.449. So we know that the root locus intersects imaginary axis at S equals to plus minus j multiplied by 2.449. And another important thing to note is we want to know the value of k at this marginal point. And what we can do is sub in omega that we get into the second term over here, and we equate that as 0. And what we have is minus 2 omega squared plus k equals to 0. And omega squared is of course 6 plus k equals to 0, and k is equals to 12. So k equals to 12 gives marginal stability. Right, so now we have everything we need in order for us to plot the root locus manually. And some of you might have noticed that I actually skip a part, which is the breakout points. And the reason why we don't need to calculate breakout points for this particular problem is that we have three poles, or three poles and one of the pole is located at 0. So basically, in the top part of the real axis, in the section over here, we only have a single pole. And we need to find breakout points only if we can observe more than a pole above the imaginary axis, or like 2 poles in the we only need to find breakout points only if there are multiple points or multiple poles on top of the real axis or multiple poles on the real axis itself. So that is when we can actually observe a condition where the root locus breaks at that point. But if you're confused, you can of course apply the formula and check the validity of the breakout points that you get. If all the breakout points that you have are invalid, that means there is no breakout points at all in the system. And so now that we have everything, let us plot the root locus. So let me prepare this. So the root locus for the second problem is, first we have found the starting points and the ending points of the root locus. The starting points are at 0 and also -1 plus minus 2.2361. So those are our 3 starting points of the root locus. And next is we find the angle of departure. First is minus 24.1 from the this pole over here. So it will go down at minus 24.1. And next we found the asymptotes, which has angle of plus minus 60 degree, and they intersect at minus 2/3. So this is where the asymptotes intersect each other, and then from this point we draw plus minus 60 degree and 180 degree. So these are our asymptotes. And then lastly, we found the intersection of the root locus with the imaginary axis, which is at s equals to plus minus j multiplied by 2.449. So here is about there, 2.449, and that is where our root locus intersects with the j omega axis. So now just complete everything. The first one is from the first starting point, go down at minus 24.1, and then intersects the imaginary axis, and then it will go to infinity following the asymptote to infinity. And then the second one, we have this pole at the real axis, and for this case it will just go to infinity along the real axis. And lastly, just do a mirror image about the real axis, and what we have is go up and cross this point and go to infinity. So this is the root locus that we have for the second problem. And we're not done yet because we have to find the closure poles for k equals to 5. And in this case, I will just substitute k equals to 5 into the characteristic equation and equate that to 0. So our CE is equals to s cubed plus 2s squared plus 6s plus 5 equals to 0. And then we get s equals to minus 0.5 plus minus j multiplied by 2.18, and s equals to minus 1. So those are the 3 roots that we get if k is equal to 5. So this is all for problem 2 of tutorial 7, and I'm going to upload another video which is covering the last problem, problem 3 of tutorial 7. Thank you.